Okay. Hello, no one. Good. So the topic today is generalized least squares. And that's short for generalized least squares estimation of GLM parameters. And the outline today is that we first do a quick review of where we are with the estimation and distribution theory of the GLM under spherical error covariances. Then we're going to discuss the motivation to go from spherical error covariance matrices to non-spherical error covariance matrices. And then we discuss the GLS, so the generalized least squares beta parameter estimator. So this bit of theory is fairly straightforward, so I suggest we just continue without a break until we are finished with the entire content. So let's first review the formulation, estimation, and distribution theory of the GLM under standard assumptions. So of course we remember by now that the GLM in probabilistic form can be seen as a multivariate Gaussian distribution over some data vector y with expectation parameter given by a design matrix times effect size beta parameter and a covariance matrix parameter of this multivariate Gaussian corresponding under basic assumptions to the product of the identity matrix, the n by n identity matrix with a positive variance parameter. So remember that this is n-dimensional, this is n times p-dimensional, beta is p-dimensional, sigma square is larger than 0. And we've of course repeatedly seen that this corresponds to this structural form where the errors are normally distributed, centered on 0, and with spherical covariance matrix corresponding to identically and independently, or independently and identically distributed error terms. Yeah? So the assumption is that the EI for I to 1 to n are ID. Now, to estimate parameters, we have seen that by means of ordinary least squares or maximum likelihood, we can estimate the parameters as follows. For beta, we have the ordinary least squares estimator given as a function of the design matrix and the data. And for the variance parameter, we've seen that we have an unbiased estimator of the variance parameter given in terms of the data, the ordinal least square estimate for the beta parameters and the design matrix. Resulting from the residual errors here squared. Now last time we've seen that from a frequentist perspective, the beta parameter estimator has a distribution, and this distribution is given by a p-variate normal distribution, which has as its expectation parameter the true but unknown value of the beta parameter, and as its covariance matrix the product of the design matrix with itself and the inverse of that multiplied by the error variance. And we've also seen that the variance parameter estimate in a rescaled version, namely multiplied by n minus p and divided by the true but unknown sigma or variance parameter, is distributed according to a chi-square distribution with n minus p degrees of freedom. And then finally what we looked at was the t-statistic, which for a given contrast weight vector merges the beta and variance parameter estimators following way. So in the numerator of the t-statistic we have the contrast weight vector CRP, which one can define as desired. We have the contrast weight vector times the beta parameter estimate minus the contrast weight vector times the true but unknown beta parameter, which ensures that the t-statistic is always centered on 0. And in the denominator we have the variance parameter estimator times the contrast weight vector times the inverse of the product of the design matrix with itself, times again the contrast weight vector, where we also notice that this here corresponds to the sigma square hat without the contrast weight vector, the sigma square hat times the inverse of the design matrix with itself corresponds to the covariance of the beta parameter. So essentially we have in the t-statistic we have a ratio between the value of a beta parameter estimate divided by an estimate of its variance. So we get a high t value if the variance of the beta parameter is estimated relatively low for a given fixed value of the beta hat parameter, and we get a low t value if the variance of the beta parameters, which is of course a function of the error variance, is high. And then we've of course also seen that the t statistic is distributed according to a t distribution with n minus p degrees of freedom. So that's basically in a couple of equations the entire GLM formulation, estimation and distribution theory. So if one is clear about this, then one is clear about a lot of things. So just as a side note, so this is model formulation here. This is model estimation. And then of course with the t-statistic we can do model slash parameter. In this case it's more parameter evaluation. Model evaluation, but it's in the evaluation stage. So that's essentially it, but most importantly, all of this is under the assumption of IID errors, which are embedded in the spherical covariance matrix. Good. So all of this holds. So these distributional properties, especially the distributional property of the t-statistics, holds if the errors are assumed to be independent and identically distributed. And the step that we are taking then today is to relax this assumption, to go from independent and identically distributed errors to correlated error terms. And the first question is why we would want to do something like that. And to this end, we now look at the motivation. And here we go to our application of interest, namely fMRI data. So remember, if you have here time, and here the MR signal of a given voxel, then what the GLM essentially does is that it comes up with a prediction of the expectation of the MR signal over time, which is encoded in the X beta, which is an n-dimensional vector. If you plot this over time, you get something like this, for example. Depending on the resolution, of course it's discrete, so I'm putting down some discrete points here. So this is the prediction, this is not observed data. It's model formulation. Now, when we talked about independent and identically errors, thus far, what we always assumed is that for each time point, we sample an additional error to the deterministic prediction. So for example, we sample here this point, and then next we sample this point, for example here, this here, this, and so on. And if we zoom a little bit in and ask ourselves, what does that actually mean that we assume independent and identical errors for all time points? We can understand this as follows. So let's say we zoom in here, and for this time point, which we call I, and for this time point j, which in this case is I plus 1, but it doesn't need to be, it can be any other time point than I, we look at the error distribution. So here we would have epsilon I, here we would have epsilon j. Now if you again think about the frequentist intuition of the GLM, we can sample observed, we can sample observed time series here, our y's, y being x beta plus epsilon, many times, which corresponds to sampling errors many times. And what we are interested in is the distribution of 2 time points over many of these repeated samples, which of course are hypothetical. We only have one observed data series in reality, but the model of course says that the epsilon are distributed, and hence we can imagine taking many samples. And for these many samples we only look at 2 time points now, at I and j. Now the IID assumption means that if we sample a large value for EI, So for example, we sample this. Maybe I make it red because that's how it is above. We sample this here for EI. Then the probability to sample a large or a small value for EJ is equally large. So if we're now thinking about having sampled EI as a relatively large value in this coordinate system, we may sample an EJ here, also a large value. But we may equally sample a low value. And this holds for all of the EI and EJ. So for example, if we have a small EI value sampled, then we have the same probability to have an low EJ or a high EJ. Of course, if you think about the normal distribution, these values that are fairly low and fairly large, if we center this whole thing on 0 here, are themselves not that likely, and what is more likely is actually to get something close to 0. So we get many more data points here, sorry, not data points, arrow points, and get less samples here. And of course this is just again representing the spherical error covariance matrix, which in analytical form we would put as a circle of isocontours for the Gaussian. Like this. Yeah, so that's the IID error case for 2 errors of our time series here. So that's about this here. Now, it turns out that if one actually does MR signaling and creates a model of the data that is based on the stimulus-induced variability. So for example, what we see above there, our observed bold response, like this, is purely due to the fact that we say there is a stimulus presented here. Yeah? So that's stimulus presentation. Now in addition to, maybe let me finish this. So here we have our discrete data points. So in addition to the stimulus-induced activity, in a biological system, we of course have many other things going on. So for example, the human participant is breathing. Breathing changes the CO2 concentration in the blood, also in the brain, and hence also affects the Bolt signal. Now we assume that we don't measure how people are breathing, so we cannot make a deterministic prediction about these errors. About the CO2 concentration changes induced by breathing. However, we know that if people are breathing in addition to the stimulus-induced activity, then on certain time points during the post-stimulus response, the CO2 concentration will be a little bit higher because people are basically getting ready to breathe again, meaning that on 2 time points following each other, the MR signal will be both higher than our prediction. So let's call this now I and J again. And now the important thing is that what we assume is that there exist these form of short-term correlations, so that neighboring errors have a higher probability to deviate in the same direction from the deterministic prediction than errors further apart. That doesn't mean they always need to be positive, it just means that errors that are close together in time have a higher probability to be correlated than errors further apart in time. So if we again look at just two of our EI and EJ, what I just said means that whenever we sample a high value for I, so for example here, then we have a higher probability to sample a high value for EJ than a low value. Yeah? And the same for low values of EJ. And roughly similar in the middle. So what this is of course referring to is a covariance matrix that predicts correlated errors that are close together in time, which if you would plot the joint PDF of two errors close together in time would look like this. Yeah, so we have a non-spherical covariation structure of two errors in time, which is induced here, this non-IID case, by unspecified systematic signal covariations close in time. Now it's very important to get clear about what this means. So if you have a model of these covariations, so if you can say, okay, people are breathing in here, so I can account for this breathing in the deterministic part, so in the X-beta part of my model, then of course the assumption that there are error correlations is not really required. Yeah. The thing is, it's not only the breathing, it's also the heartbeat, it can be motion artifacts. So the idea is that there are many things that can induce correlations in the error terms, not all of which can be recorded. However, that said, this serial error correlation business was dealt with in the 90s, early 2000s, when people actually didn't have the means to collect a lot of other physiological data with the scanner as they have now. So for example, now we can record the breathing with a breathing belt, or monitor O2 with an oximeter, and we can monitor the heartbeat with an ECG. So you now often see that people, based on these physiological parameters, create regressors that they include in their GLN. And then, of course, modeling error correlations becomes somewhat obsolete. However, often it's still done to account for any form of residual correlation. Yeah. So it can't hurt. Of course, you can maybe describe things better if you put them into the model in terms of the deterministic prediction, so in the design matrix. But if worse comes to worse, the correlation structure of the errors is estimated as being spherical, so IID, and then you have lost nothing if allowing for the fact that you might have serial correlations. Yeah. So that's serial correlations, error serial correlations, and its motivation from the fMRI perspective. And we will get back to this now when we, of course, when we first discussed the general least squares estimator, but then also the variance component estimation that, for example, happens in SPM together with REML estimation. So we will get back to that and talk about models for the error correlations again. Today, the only thing I want to achieve is to basically go from the scenario that we have a spherical covariance matrix to a scenario where we don't have a spherical covariance matrix, so where we have a matrix V, which is symmetric and positive definite, so that we have a proper variance parameter, but yeah, we don't talk about its details, and the most important thing is that it's not the identity matrix, so V is just not IN. Well, and we will get back to close our more specified and more specific error covariance matrix parameters soon. However, to get started with the whole thing, we now essentially assume that our error covariance matrix is not the identity matrix times sigma square, but a non-identity matrix, positive definite, and we look at the effect. So the first thing that happens if you have such a scenario is that, of course, this assumption of the GLM is violated. Yeah, so it just doesn't hold anymore, and hence there is no guarantee that specifically the estimator formulas or the distributional properties of these estimators hold. And this can be fairly straightforwardly visualized, and this is what I want to show you next when talking about the t-distribution, because this is, of course, essentially what people are most interested in, because this is essentially the result of a study. So what we have here on the left side is a spherical covariance matrix for 10 data points. I think it's a simple linear regression design. 10 data points, and data was sampled from this GLM, and like we saw last time, the t-distribution was evaluated, and its histogram was evaluated over these repeated hypothetical samples. In this case, these were real samples taken on a computer, of course. Histogram was evaluated and compared to the t-distribution for 8 degrees of freedom, because it's 2 parameters in the simple linear regression design, so n minus 2 is 8 degrees of freedom. And we see that this fits, and so the distributional theory of the GLM holds. Now, in this case, we look at a covariance matrix that actually encodes some form of correlation in neighboring time points. So, for example, if you look here, 1 and 2, 1 is, of course, self-correlated, or basically representing its variance, but then in 1 and 2, and so 2 and 1 as well, also show non-zero correlation. And this holds for all of these time points. So, for example, here, say this, 6 and 5 and 6 and 7 are also somewhat correlated. Now, if we look at the t-values that result from sampling this and compare it to the t-distribution that is supposed to hold, in this case, we see the following. We see that we have definitely more high and very low t-values than predicted by the density of the t-distribution. Yeah? So we get samples t-values here where the t-distribution says the probability is actually quite low. So in reality, if we have something like this, we have a higher probability of observing something here than predicted by the model. So we increase our false positive risk if we use the t-distribution for statistical testing. Yeah? So essentially the bottom line of this is, if you have in the presence of error correlations, because the actual distribution of the t-statistic doesn't follow the theoretical distribution of the t-statistic anymore, you increase your risk for false positives. So one way to view that is, of course, if you have error correlations, you have less independent data points, so you essentially reduce the number of data that you have compared to the theoretical amount of data that you have, which is given by the number of data points minus the number of parameters. And because you reduce this, you have less data, and hence you become overconfident in your results. This can be looked a little bit more closely. So, of course, this is at the level of the t-statistic, where all of the assumptions and the distributional properties of the GLM are already summarized. If one looks a little bit more closely to where things are going wrong, then this is also quite insightful. So we briefly now look at the non-spherical errors. Effect on beta parameter estimation. And to think about this, we first look at the expectation of the beta parameter estimate, which is of course given by the expectation of the formula for the beta parameter estimate, which then with the linearity of expectations can be rewritten as this, which then, because the expectation of y is of course the design matrix times the true but unknown parameter value, is better. So what we see in terms of the spherical error effect, there is none on the expectation of the beta parameter. So it's not that the beta parameter estimates get biased by the non-spherical errors. But what happens is that the covariance matrix of the beta parameter estimate changes. So you might remember that from the linear transformation theorem for Gaussian transformations, what happens here is that we need to transform the covariance matrix of the data by the transformation matrix, and then we get the, so let's call this beta hat, and this sigma y, then we get the covariance matrix of the beta parameters. So we did that last time. Now, if we start not from the spherical covariance matrix, but now from the non-spherical covariance matrix, the formula in the linear transformation theory for Gaussian distributions evaluates like this, and what we get is this statement. And last week we had here for v we had in, and then we ended up at this covariance matrix for the beta parameter estimator, but here we have v doesn't equal the in, so we definitely don't get there. Yeah, so that doesn't happen. So our covariance matrix, if we assume non-spherical errors, is not the covariance matrix that enters here, and hence the distribution of the beta parameter estimate, this one, is not as it is supposed to be in the case of spherical errors, which also then means that the t-statistic is definitely not guaranteed, as we've already seen in terms of simulations, according to a t-distribution, because this is based on this covariance matrix parameter. Yeah? So what do we have essentially as results of error serial correlations? First, our error covariance, let's maybe do it like this, the error covariance is not this. This is of course the basic thing, that the data are not IID. And then we have that the covariance of the beta estimate is not this, from which it then results that the t distribution, as we've already seen, is not distributed according to this. Yeah, so that doesn't hold. And I mean, it could go either way, but as we've seen, because we effectively reduce the data that we have compared to by means of error correlations compared to what we think, how much data we have, we increase our false positive risk. So these are the consequences if we have non-spherical data. So we have to somehow account for the fact in the estimation theory. Yeah. So if we have good reasons to believe that we don't have spherical errors, then we should not use simply our theory on our theoretical results that come out under spherical errors, but we should build in the fact that we have non-spherical errors. And this will be then, after all, the topic for the next hour to introduce the generalized least squares beta parameter. So let's have a brief break.